Hi guys, today we're looking at vertical circular motion. So we're going to look at the forces that can cause centripetal motion. So when an object is moving at a constant speed in a vertical circle, the centripetal acceleration and the centripetal force must be constant. So we have a constant force pushing inwards. So we're going to use our example as a bucket swinging vertically on a string. So we know that our centripetal force must be constant, but the forces that cause the circular motion can change. Okay, so let's take our bucket on a string. While the bucket is swinging on the string, we're going to look at the centripetal force at points A, B, C, and D. Let's have a look at the forces that are acting on a bucket as it's swinging in a circle. So please remember that the centripetal force will always be a constant value at each point. So that doesn't change. So it's a constant value. Okay, so let's just say it's always 5 newtons. Let's look at the forces acting on the object at point A. So when the bucket is overhead, we have 2 forces acting on it. We have mg, which is the weight of the bucket, which will also stay constant. The weight is given by ng, so let's just say it is 3 newtons. And what other force is acting on the object at this point? Well, there is also a tension on the string that's pulling the object down. These 2 forces added together will give us our centripetal force. So at point A, our centripetal force is caused by the weight of the bucket plus the tension on the string. At point A, can you work out what the tension on the string would be? So we can see here, if our centripetal force is 5 newtons, the tension must be 2 newtons on the string to provide that centripetal force of 5 newtons towards the centre. All right, let's look at the forces that are acting on the object at point B. So again, we have 2 forces acting on the object. So that's the tension on the string and the weight. So the tension on the string is still the force that is pulling the object in. The weight is acting downwards. So in this case, the weight has no effect on the centripetal force. Therefore, at point B, our tension is equal to the centripetal force. Can you work out what's the tension at point B? So the tension at point B must be 5 newtons, as the tension is equal to the centripetal force, which we know is 5 newtons. Okay, let's have a look at the forces acting on the object at point C. So again, we have our weight of our object, the weight of the bucket, which is acting downwards, and the tension on the string is causing our centripetal force, which is acting up. At point C, the tension in the string needs to overcome the weight of the bucket. Can you work out what the tension must be in this case? We know that our centripetal force must remain as 5 newtons. Our weight is 3 newtons. Therefore, we should see that our tension is greatest at point C. It needs to be 8 newtons to provide a resultant 5 newton centripetal force. Okay, let's look at point D. So point D is the same as point B. At this point, the weight is acting downwards. The centripetal force is perpendicular to this. So in this case, the centripetal force is equal to the tension on the string. These are the forces that are acting on the bucket at points A, B, C, and D. At point A, the tension is the smallest because part of the centripetal force is caused by the weight also. So at A, our centripetal force, mv squared over r, equals our weight plus the tension. At point C, the tension is the greatest because it must hold up the weight as well as the centripetal force. In this case, our centripetal force is equal to the tension, so however big your tension is, minus the weight, minus your weight. At point B and D, the tension provides all of the centripetal force as the weight is perpendicular to the tension. So at B and D, your centripetal force is equal to your tension. From this we can see that our centripetal force, let's just say that stays at 5 newtons. So the centripetal force will always be 5 newtons. The forces causing the centripetal force can change. Let's say that our weight of our bucket is equal to 3 newtons. Our tension, therefore, must be 2 newtons to make up our constant centripetal force of 5 newtons. At point C, if our weight is 3 newtons, the tension is 8 newtons, which still gives us a centripetal force of 5 newtons. At point B and point D, the tension is 5 newtons because it is equal to the centripetal force. Please pause and take this down. Let's look at the following example. Consider the forces acting on a roller coaster at the top and the bottom of its motion. Can you write an equation describing the centripetal force similar to our last example? The centripetal force in a roller coaster is caused by 2 things: the force of gravity and is supplied by the track pushing normal to the track surface. So there is a force applied by the track itself pushing normal to the track surface. Okay, so we have a force, we'll call it your engine force, or you can call it your normal force. So that's the force that causes the object to move around. So at point B, we know that our engine force must be smallest, as most of that centripetal force, the force causing the object to move in a circle, is provided by the weight of the roller coaster. Whereas at point A, the rate of the roller coaster acts in the opposite direction of our centripetal force. Therefore, our engine force at this point must be much greater